of what I meant to say Ethernets. It was first one was called bridged Ethernet. So Ethernet that is connected through bridge. Basically, most of the Ethernets were having a bus topology. Now, when you connect two, LANs, two separate LANs using a bridge, it's bridge. The effect of adding a bridge in between two different LANs is the collision. What I'm saying, domains were separated, and the bandwidth was increased. So two functionalities were achieved through the introduction of a bridge between two separate LANs, right? So we will see in the next slide how introduction of a bridge helps, what I mean to say, uh, in increasing the bandwidth of the network, and again separating the collision domain. So how it increases the bandwidth? So here, if you see this diagram, in this case, the diagram is something like this. If two stations are there, I mean to say, assuming this is the scenario, right? So this is the scenario, this is the bus topology, and suppose this is the end of the cable, this is also end of the cable, and the systems are connected like this. Systems are connected like this. So I have one system here, I have one system here, I have one system here, right? And I have one system here and one system here, and assuming that there is one system here. So total, bandwidth is 10 Mbps, right? 10 Mbps, and there are 6 systems that are connected. So now, assuming that at any point of time, say two systems, this system is sending the data, and this system is sending the data. So as we know, at a time only one system can send the data. The bandwidth allocated to this, this thing will be only 5 Mbps. Like one frame. You can see here, one frame is being sent, and then it has to wait. Then during this wait time, another. Yokita Ravindran, this is the second day that I am getting the disturbance. Okay. So during this gap, the other frame is released by other station. So this station will release its frame, and then next this is released. First station release the frame, and then second station release the frame. So during the gap time, you can see the stations are releasing their frames. So effective, though it is 10 Mbps, it is divided into 5 Mbps. So if assuming that all the systems are sending and receiving the data, in that case, it will be 10 Mbps by 6 systems. You got the idea? So the bandwidth is reduced. It is shared amongst all these what I would say units. Now assume another scenario. I have some scenario like I introduce a bridge in between. I introduce a bridge somewhere here. So this is the bridge. You got the idea? This is the bridge. Right. So this is the bridge that I'm introducing in between here. And you can see here the collision can occur anywhere in the cable. Collision can occur anywhere in the cable. So collision domain is this entire cable is the collision domain. So this is where the, this is the end point of the cable, and this is also end point of the cable. This is again bus topology here and bus topology here, and the systems are somewhere connected like this. So this is one system, and this is second system, and this is a third system, right? And this is again one system, and this is another system, right? And this is one more system. So here you can see this part is a separate LAN. This part is a separate LAN. You got the idea? So I can call this as LAN 2, and this I can call it as LAN 1. You got the idea? This I can call it as LAN 1, right? LAN 1. So this is again, it will have 10 Mbps. You got the idea? It will have 10 Mbps. 10 Mbps, and this will also have, this LAN 2 will also have 10 Mbps. 10 Mbps. So this is the biggest advantage of a bridged, Ethernet. So here, if two stations are sending the data, in that case, you got the idea. This entire 10 Mbps is available for these three systems. So in this scenario, this 10 Mbps was available for these all six systems taken together. Here, 10 Mbps is available to three systems and 10 Mbps is available to these three systems. So here I can see clear-cut divide. Bandwidth is increased. Definitely, bandwidth is raised in this case. Bandwidth is raised. And the second point we had was separate collision domain. So any collision that would occur, it will occur here, and any collision that would occur, it will occur here. So collision domain. So this I can take it as domain 1, and this I can take collision domain 2. You got the idea. This I can take collision domain 2. So collision domain is also separated, but in this scenario, bus topology, the entire this thing is taken as a collision domain. This entire thing is taken as a collision domain. So this was something about what I meant to say. um this particular bridged Ethernet. Now we had what I meant to say. This is the, of course, this is what I had explained. Now this is the diagram. That is what I was trying to explain. So here, this is a bus. You got the idea, having six systems and six total 12 systems. So bandwidth is nothing but taken as 10 Mbps divided by 12. So literally, the systems are getting less than 100 Mbps each, 100 Mbps each. Whereas when I have connected separated these LANs, so six systems here and six systems here, and in between, if I introduce a bridge here, so this LAN gets separated and it can use 10 Mbps here and 10 Mbps here. And the collision domain is also separated. Bandwidth is enhanced. Now 10 Mbps is divided into six systems. So it is definitely more than 100 Mbps for each system. So this is the biggest advantage of bridge, what I meant to say, this thing. And collision domains are separate, um, right? And this is another arrangement of bridge. So if you want to reduce the collision domain further, still further, see here what I have done is this LAN, this is domain 1, domain 2, domain 3, and domain 4. Now here the entire this LAN will have a 10 Mbps, this LAN is having 10 Mbps, this LAN is having 10 Mbps speed, and it will support data rate of 10 Mbps. Now 10 Mbps is divided amongst only three systems. So 10 divided by 3. So more than 300 Mbps, 300, roughly 333 Mbps of data rate each station is allocated. And the collision domain is highly reduced here. Collision domain is highly reduced here. In this scenario, entire what I'm say, this topology itself is a collision domain, complete collision domain. But here, collision, if it occurs over here, these three domains remain unaffected. You got the idea. So here, if what I mean to say, collision occurs anywhere in this bridge, what will happen is all the systems will have to stop sending the data. Right, but here, if a collision occurs here in this particular domain 2, I said this is domain 1, domain 2, and this is domain 3 and domain 4. Collision occurs in domain 2, this particular domain. So what will happen is the effect of the collision is restricted to this domain only, and these domains still can transmit the data across, except this domain, except this domain. So that is the biggest advantage of separating the collisions through a bridge. This was something about bridged Ethernet. Then we had next was switched Ethernet. The idea of bridge LAN could be extended to switch LAN. So instead of bridge, now we will have something called as switch, right? So instead of having 2 to 4 networks, why not have the concept came like this? Why not have n networks? Right. So n is the number of stations. So if 10 stations are there in the network, so there let it be 10 domains. 10 separate domains connected through switch. So if a switch is to have what I meant to say, 10 different domains. So many ports should be there connected to switch. So switched Ethernet was very, advantageous. So it was a multiple port bridge kind of thing, and it was N port switch. So bandwidth is shared only between the station and the switch. You got the idea? So each station gets 5 Mbps of data. So that, and collision domain is divided into N domains. We will see in the, what I meant to say, this thing. So layer 2 switch is N port bridge we have got, and this is the diagram. You can see here how many systems are there: 1, 2, 3, 4, 5, 6, 7. And this particular thing is what I mean to say, 9 port switch. So 9 port switch means this is 333. 9 domains could have been there. Now here the each domain will have a speed of 5 Mbps. That means this system can transmit the data at the rate of 5 Mbps. This is 5 Mbps. This is 5 Mbps. This is 5 Mbps. This is 5. This is 5. So you can see here the bandwidth is quite increased. You got the idea. And the collision domain is again number of systems is forming a network with the switch. So this is a separate network, and this is separate network. This is separate network. So the collision, if at all it is there, it is within this particular network and the switch. And these remain unaffected. These remain unaffected. So in earlier system, at least 3 systems were there where we got the idea, and a bridged Ethernet. At least 3 systems were there that were getting affected, but here only 1 system is getting affected if collision is there, if collision is detected. So remaining all systems are still, available for communicating, sending the data, transmitting the data, and receiving the data. So this is the biggest advantage of a switched Ethernet over hub-based bridged Ethernet, bridge-based Ethernet, and that had us, very good advantage over, 10 base 5, 10 base 2, and all. So this is about, switch-based Ethernet. Now we have next thing is full duplex Ethernet. So the biggest disadvantage of 10 base 5 and 10 base 2 was the communication was half duplex. Means, half duplex means the twisted pair cables were there, but either they could receive the data at a time or send the data at a time, but not both receive and send the data at the same time. So biggest disadvantage that was associated with 10 base 5, that is thick net, and 10 base 2, which is thin net or cheaper net, right? Was half base, half duplex communication. And 10 base T is always 10 base T means twisted pair cable is always what I meant to say, full duplex communication. Full duplex communication means separate cables were there for receiving the data and sending the data, right? So here, full duplex switched Ethernet was the next development, and capacity of each domain was raised. I mean to say, bandwidth was raised from 10 Mbps to 20 Mbps. Now you see here, as the advancements happened in the Ethernet, the bandwidth went on raising, and the collision domains went on depleting, means decreasing. So this is what I meant to say. Instead of using one link between the station and the switch, configuration uses 2 links, one to transmit the data, one to receive the data. So here you can see this switched Ethernet only, but it is called as full duplex, Ethernet. So in this full duplex, there is a switch only, and these are the, this is domain 1, this is domain 2, this is domain 3, domain 4, domain 5. And here the bandwidth is allocated to this system is 10 Mbps and 10 Mbps. That means at the rate of 10 Mbps, it can send the data, receive the data at 10 Mbps. Total capacity is 20 Mbps. Here also it is 20 Mbps, 20 Mbps, 20 Mbps. So this is the biggest advantage of full duplex switched Ethernet, right? So, and there was no need for, you have seen in 10 base T and, 10 base 2 and 10 base 5, you had seen the, sensing, carrier sensing was being used. So before sensing, to avoid the collision, avoid the collision, CSMACD means the moment collision is detected, a station is supposed to desist from sending the frame. So CSMACD was there. But in this particular arrangement of full duplex switched Ethernet, there is no point of having CSMACD because there is a separate line for transmitting the data and separate line for receiving the data. So CSMACD is done away with completely. It is not needed at all. Not needed at all. Right. So and each link was a point-to-point connection, was having point-to-point connection between the host and the switch. Right. So no longer carrier sensing was required. So if any station wanted to send the data, it should send it to switch. Switch will, see to which, what I meant to say, station the data should go, incoming data should go. So it will transfer the data to that particular station because each station had separate line for receiving the data, separate line for sending the data. Right. So here the job of a MAC layer became very easy. Means since there was no CSMACD to be done, and we had seen collision carrier sensing and collision detection functionality in the MAC sublayer were to be switched off. It is not needed because of presence of two cables, two different cables, right? So we have seen standard Ethernet was designed as a connectionless protocol. Connectionless protocol means, again, I'll tell that if a sending station has a what I'm saying frame to send without bothering about the processing capability of the receiving host, it keeps on pumping the frames through the medium. So it was a connectionless protocol at the MAC sublayer. And there is, we had seen standard Ethernet had not defined exclusively the flow control mechanism or error control mechanism to inform the sender that a frame has arrived without error, or frame has arrived with what I mean to say error. No information was given by the receiver to the sender. Right. Simply, it will drop the packet if what I meant to say, if this thing. But for switched, what I meant to say, full duplex switched Ethernet, this flow control error control were to be provided actually. So there was for doing so, for providing flow control and error control into full duplex switched Ethernet. I got the idea. A separate sub layer was added called as MAC control. And through this MAC control, it was added between the logical link control and MAC sublayer. And it was, this MAC control's job was to incorporate flow control and error control into full duplex switched